Here everything other concepts are same as other blocks properties. Here we know electrons are getting increased, protons are getting increased, and as well as the atomic number will also get increased. You can observe lanthanoids having similar properties, but it will react with almost with all the reactivities. Some of the tripositive ions are colorless. Here some of the tripositive and tetrapositive ions are colored. These are the major differences between lanthanoids and actinoids. Hello everyone, this is Harshita Bhavasar from Vidhyaashram PU College Temple of Excellence. This is the last session of D and F block elements. In the previous session, we have discussed about potassium dichromate and potassium permanganate, its physical and chemical properties and its importance. And in the current session, we will discuss about the F block elements. Overall, the position of F block elements in the modern periodic table, its electronic configuration as well as its preparation, and the difference between lanthanoids and actinoids. The 28 elements from atomic number 58 to 71 and from atomic number 90 to 103 are arranged in two horizontal rows below the periodic table. In the previous session itself, I have showed that overall periodic table picture. Last two series of D block has been separated and they have kept below the periodic table. Those two series will be considered as F block elements. The first series will be having atomic number 58 to 71 will be considered as lanthanoids, and next series 90 to 103 will be considered as actinoids. Those two lanthanoids and actinoids will be considered as F block elements. The elements in which the last or differentiating electron enters the penultimate energy shell, that is N-2F, are called F block elements. The elements are also called inner transition elements because N-2F subshell is lie comparatively deep within the kernel. Okay. In lanthanoids, 4F subshell is gradually filled with the increase in atomic number, hence they are called elements of 4F transition series. In actinoids, 5F subshell is filled, hence they are called elements of 5F transition series. And these inner transition series will also call it as rare elements. Because of lanthanum, a member of 5D series closely resembles the lanthanoids, it is usually included in the discussion of lanthanoids. For similar reasons, actinium is included in the discussion of actinoids. The first element is present, lanthanum. The overall series will be called it as lanthanoids. The next series, the first element will be actinium. So, the overall row will be called it as actinoids due to the resemblance in the properties. First, we will discuss about lanthanoids. That is, 4F series include 14 elements from the cerium to lutetium. In these elements, 4F subshell is gradually filled. These elements constitute the first inner transition series. Lanthanoids will start from lanthanum, next cerium to lutetium. Its atomic number will be 58 to 71. Electronic configuration: after xenon, 4F 1 to 14, 5D 1 to 10, 6S, 4D 1 and 6S 2. Okay, we will discuss about atomic and ionic radii. There is a special property called lanthanoid contraction. Why we will call it as lanthanoid contraction? In lanthanoid series, there is a regular decrease in the atomic size as well as in the ionic radii of trivalent ions as the atomic number increases. In the trivalent ions, as the atomic number increases, there is a gradual decrease of atomic as well as ionic radii. That concept will be called it as lanthanoid contraction. The gradual decrease in size of lanthanoid atoms and ions with increase in atomic number is called lanthanoid contraction. Next, causes of lanthanoid contraction. Why this lanthanoid contraction will happen after that atomic number is also increasing? The major cause for lanthanoid contraction is due to the poor shielding effect of 4F electrons. You know about shielding effect, but here poor shielding effect is presenting by 4F electrons. As we move along the lanthanoid series, the atomic number increases. The number of electrons and protons present in atom also increases by 1. In the lanthanoid series, as we move one by one, the atomic number obviously increase, their proton, electron will also increase by 1. As electrons are being added to the same shell, the effective nuclear charge increases. The 4f electrons have poor shielding effect, therefore the effective nuclear charge experienced by the outer electrons increases. Okay. Here everything other concepts are same as other blocks properties. Here we know electrons are getting increased, protons are getting increased, and as well as the atomic number will also get increased by 1. But it will be happen in same shell, so it will be facing poor shielding effect and effective nuclear charge experienced by the outer electrons increases. Consequently, the attraction of the nucleus for the outermost electrons increases. Here, the attraction of nucleus by the outermost electrons will increase. This results in a steady decrease in the size of lanthanoids. So, by that attraction of nucleus by the electrons, here the size of lanthanoids will keep on or gradually decrease with increase in atomic number. This is termed as lanthanoid contraction. Contraction means the suspension of size or suspension. So, here lanthanoid side will be contracted, so it will be called as contraction. Next, consequences of lanthanoid contraction. What will happen after lanthanoid contraction? There is similarly in the properties of second and third transition series. After the lanthanoid contraction, there is a similarity between second and third transition series. Separation of lanthanoids is possible due to the lanthanoid contraction itself. It is due to the lanthanoid contraction that there is a variation in basic strength of lanthanoid hydroxides from lanthanum to lutetium. Okay. After the contraction, there is a similar property of second and third transition elements, and also separation of lanthanoids will be possible easily by the after the lanthanoid contraction, and also due to this effect, variation of basic strength of lanthanoid hydroxides can be seen. These are the three consequences seen from lanthanoid contraction. Next, oxidation states. Lanthanoid elements show a common oxidation state of +3. The oxidation states of lanthanoids are given in table. Some elements will show +2 and +4 also. Common oxidation state of lanthanoid is +3. But some of the elements will show +2 and +4 state in solution or solid compounds. This irregularities arise due to the extra stability of empty F subshell, half-filled subshell and completely F subshell. Usually +3, rarely +2 and +4 in solution and solid state. Why this will happen? Because sometimes empty F subshell will be present, half filled F subshell will be present, sometimes completely filled F subshell will be present. And those subshells or exceptions are europium, which is having atomic number 63, and ytterbium, which is having atomic number 70, given oxidation states of +2 in addition to +3, because europium 2+ has half filled subshell and 4F7, and ytterbium +2 has completely filled subshell, that is 4F14, would be exceptionally stable. Okay. Next, cesium, which is having atomic number 58, and terbium, which is atomic number 65, given oxidation state of +4 in addition to +3, because cesium +4 has the empty F subshell and 4F0, that is Tb +4 half filled subshell is 4F7, would be exceptionally stable. Once again, usually it will be having +3 oxidation state, rarely +2 or +4. Why it will happen means because sometimes empty F subshell, half filled subshell and completely filled subshell can be seen. In the europium and ytterbium, oxidation state +2 and +4 can be seen, or else in the cesium and terbium can be seen with empty subshell and half filled subshell can be seen. These are the exceptions. However, it is observed that elements have neodymium, promethium, samarium and thulium give an oxidation state of +2 also, and the elements of protium and dysonium give an oxidation states of +4 also in addition to +3. These cases cannot be explained on the basis of rule of extra stability. However, these states are unstable and tend to revert to the most stable oxidation state. Whatever we have seen in the exceptional case, it will not follow the extra stability rule, and those whatever it will have the oxidation state are completely unstable, and it will come back to the most stable oxidation state again, that is +3. In case of oxidation states of lanthanoids, the following points may be carefully noted. The +2 and +4 oxidation states tend to revert to the more stable oxidation state of +3 by loss or gain of electrons. Whatever we have seen the rarely or exceptional case of oxidation state, that is +2 and +4, they are not completely stable, so it will be revert back to the original or +3 oxidation state by losing or gaining of electrons. Samarium 2+, europium 2+, and ytterbium 2+ ions can lose an electron and hence are good reducing agents in solutions. These three elements, by losing its electrons, it will be good reducing agents. Cerium +4 and terbium +4 etc. ions can gain an electron and hence they are good oxidizing agent. By losing the electrons, those three will be good reducing agent. By gaining electrons, these two will be are good oxidizing agents. And protium, this will be terbium and dissocium, exhibit having +4 oxidation state only in oxides. So these are the oxidation states of lanthanoids with variable with the definitions. And after having the variable oxidation state, what property it will show? See here, lanthanum +3, cerium +3 +4, protium +3 +4, neodymium +2 and +3, and protium +2 and +3, samarium +2 +3, europium +2 +3, gadolinium +3, terbium +3 and +4, dioxinium +3 and +4, and holmium +3, and erpium +3, and this is thulium +2 and +3, ytterbium +2 and +3, lutetium +3. Usually always +3, this +2 and +4 are exceptional cases. Next, chemical reactivity. All the lanthanoids have almost similar chemical reactivity. The metals readily tarnish in air on heating in oxygen to form oxides type of M2O3. Usually lanthanoids will having similar chemical properties. When it is reacted with oxygen, it will form oxides, that is M2O3 oxide. They react with hydrogen at about 300 to 400 degrees Celsius to form solid hydrides of the type MH. All the lanthanoids will almost all react with solid hydrides at the temperature called 300 to 400 degrees Celsius, and it will form hydride called MH. When heated with halogen X, they give halides type of MX3. Okay, they give carbides of the M3C and M2C3, MC2 when heated with carbon at 2773 Kelvin. See here, M3C, M2C3 and MC2. Those are all carbides, that is halides, and here metal hydrides, here metal oxides can be seen. When treated with dilute acids, it will liberate hydrogen gas. At elevated temperatures, they combine with nitrogen, sulfur, phosphorus, antimony and bismuth. With sulfur and nitrogen, they give sulfides and nitrates. It will give. They react with water to form hydroxides with the liberation of hydrogen gas. Here you can observe lanthanoids having similar properties, but it will react with almost with all the reactivities with water to form hydroxide, with to give sulfides, nitrogen, nitrates, and which also liberate hydrogen with acids and also form carbides, halides, hydrides and oxides. So these are the chemical properties of lanthanoids. Next, actinoids. Those are all 5F series including 14 elements from thorium to lawrencium. In these elements, 5F subshell is gradually filled. These elements constitute the second inner transition series. Most of the elements, that is elements beyond uranium, are prepared synthetically in the laboratory through nuclear reactions. After uranium, almost all the elements are synthetically made or prepared through nuclear reactions in laboratory. The starting element of this purpose is always uranium. Hence, these elements are from atomic number 93 to 1 or 3, that is from neptunium to lawrencium, are called transuranic elements or uranites. The starting element will be uranium, so we will call it as transuranic elements or uranites. All the actinoid elements are radioactive in nature. It has been prepared or synthetically made in laboratory through nuclear reaction, so it will be radioactive in nature. General electronic configuration of actinoids is radon 5f1 to 14, 61 and 7s2. Ionic sizes decrease in size due to the increase in effective nuclear charge on the outermost shell and poor shielding effect by 5 electrons. It is referred as actinoid contraction. We have discussed already about lanthanoid contraction. This will happen due to the poor shielding effect of 4f in lanthanoids. Here also same thing you can see, that is actinoid contraction. As the atomic number increases, the size of atom will decrease and ionic radii will be decreases due to the poor shielding by 5f electrons. That effect will be termed as actinoid contraction. Next, oxidation state. Actinoids exhibit a larger range of oxidation states. This is due to the fact that 5f, 60 and 7s levels are comparable energy. Here variety of or large range of oxidation states you can observe due to the variable or comparable energies of 6d, 5f and 7s levels can be seen. The known oxidation states of actinoids are given here. Actinium plus 3, thorium plus 3 plus 4 and protactinium plus 3 plus 4 and plus 5, uranium plus 3 plus 4 plus 5 plus 6, neptunium plus 3 plus 4 plus 5 plus 6 plus 7, plutonium plus 3 plus 4 plus 5 plus 6 plus 7. These are having majorly high range of oxidizing agent. And americium plus 2 to plus 6, next curium plus 3 plus 4, berkelium plus 3 and plus 4, californium plus 2 plus 4, like that till lawrencium plus 3, but major having large oxidation state is neptunium and plutonium having plus 7 of oxidation state, which is having a variable oxidation state. Next, physical and chemical properties. The actinoids are highly reactive when they are finely divided. They are highly reactive in nature. Actinoid, when treated with boiling water, it will form oxide and MH, and that is a hydride. Actinoid plus non-metal at the moderate temperature, corresponding compound. Actinoid plus hydrochloric acid, oxide layer. Actinoid plus nitric acid, which is also a metal oxide. Actinoid plus basic, no reaction, means actinoid only react with boiling water, non-metal and acid, not reacting with base. Metallic radii of actinoids is more as compared to lanthanoids. Next, comparison of lanthanoids and actinoids. What are the similarities between the lanthanoids and actinoids? We'll see. Both lanthanoids and actinoids are F block elements. They involve in the filling of F subshell in anti-penultimate shell. Both lanthanoids and actinoids will belongs to F block elements and they involve in the filling of F subshell at anti-penultimate shell, that is N-2 F subshell. Both can be represented by the same general electronic configuration. It has same general electronic configuration. Lanthanoids N equal to 6, for actinoids N equal to 7. That is the only difference. In the atoms of both the series, 3 outermost shells are partly filled while remaining shells are completely filled. The elements of both the series show mainly +3 oxidation state. Mainly actinoids and lanthanoids will show +3, remaining are exceptional cases. The elements of both the series are electropositive in nature. They are reactive metals act as strong reducing agent. They are mainly electropositive in nature. They are highly reactive metals and they show the strong reducing agent property. In the series, as atomic number increases, there is a decrease as well as ionic radii. There is a contraction called lanthanoid contraction and actinoid contraction in both the series. Most of the cations of both these series are colored. Cations having same number of unpaired electrons have nearly same colors. It will show colored series also when unpaired electrons are present. In case of both these series, the nitrates, perchlorates and sulfates of trivalent cations are soluble while hydroxides, carbonates and fluorides are insoluble. Both lanthanides and actinides exhibit ion exchange behavior. Okay, here you can observe the ion exchange behavior from both actinoids and lanthanoids. These are the similarities between lanthanoids and actinoids. Now, we will see the differences between lanthanoids and actinoids. Lanthanoids, except promethium, all the lanthanoids are non-radioactive. Here all the actinoids are radioactive. Due to the preparation by nuclear reaction, here all the actinoids are radioactive. Here except promethium, all are non-radioactive. In addition to +3 oxidation state, lanthanoids will show +2 and +4 oxidation states also. Here in addition to +3, +2, +4, +5, +6 and till +7, the oxidation state can be carried out. They do not form oxo ions, but they form oxo ions such as uranium, oxo 2+, this one plutonium and etc. These ions are stable in acids and aqueous solutions. Their oxides and hydroxides are less basic. Here oxides, any hydroxides are more basic. They have low tendency to form complex compounds. They have high tendency to form complex compounds. Their paramagnetic nature can easily be explained. Here their paramagnetic nature cannot be explained easily. The observed values usually do not tally with expected values. Some of the tripositive ions are colorless. Here some of the tripositive and tetrapositive ions are colored. These are the major differences between lanthanoids and actinoids, which is very much important for the examination purpose. Next, applications of D and F block elements. Iron and steel are important construction materials. Their production is based on reduction of iron oxides, removal of impurities and addition of carbon and alloying metals such as chromium, manganese and nickel. Okay, due to the iron and steel. Next, titanium oxide is used in pigment industries, coloring industries. Manganese dioxide is used in battery cell, also zinc and nickel or cadmium in the batteries. Elements of group 2 are coinage metals. Vanadium pentoxide catalyzes the oxidation of sulfur dioxide in contact process. Iron catalyst is used in Haber's process. Titanium chloride and aluminium chloride forms Ziegler-Natta catalyst. Usually they show catalytic property, we know that. Nickel complexes are used in polymerization of alkynes. These are the major applications of D and F block elements. This completes the chapter called D and F block elements. I hope you have understood completely whatever I have taught today. D and F block elements are very much important chapter from the inorganic part. So study well. We'll meet in the next upcoming new chapter. Till that, thank you.